Good day class. In this video, we will find out how to find the power which is present in the wind.
Now, we are trying to find out and convert energy from the wind into useful motion. For that, we have to first understand what is the power in the wind itself. So, let's say consider a packet of air with mass m moving at a speed of v. So, its kinetic energy Ke can be given by the familiar equation Ke is equal to half mv square. Power is equal to energy per unit time. So I can say that the power represented by a mass of air moving at velocity v through an area A. So this, let's say, is a cross sectional area A. This would be equal to energy by time, and we can say this is half times mass by time v square. I've just rearranged this term along with this m here. So we have a term here called mass by time. So we define the mass flow rate m dot through an area A as the product of air density rho, speed v, and cross sectional area A. So what we get here is that m dot is equal to mass per time is equal to rho times A times velocity. So once we have defined the mass flow rate, we can use mass by time into the power of the wind. The power in the wind Pw is now defined as half times rho times A times velocity v into v square, or it's equal to half times rho times A times v cube. In this equation, we have the Pw is the power in the wind in watts. Rho is the air density in kg per meter cube, and the typical value here is 1.225 kg per meter cube. So A is the cross sectional area and V is equal to the wind speed, which is normal to that cross sectional area in meter per second. Now what if I don't know what is the cross sectional area? Let's say I just want to find the power in the wind. I don't know how much area it's going to cover. So we define another term called specific power. This we define it as Pw over the cross sectional area. So what we get here is that the specific power is equal to half times rho times v cube. So if you are asked to find out the specific power in wind, if you don't know what the cross sectional area it is going through, then you just use this equation, which is half times rho times velocity cube. We have to understand the wind speed and power with respect to it. We can generate useful power for wind speeds between cut-in wind and cut-out wind. Now what are these terms defined as? The cut-in speed is defined as the minimum wind speed at which the wind turbine will generate usable power. So what it means is that only after a certain amount of wind speed I'll be able to get some usable power from the wind turbine, which also means that any speed lower than here, lower than this point, all the power here utilized for overcoming all the losses in the wind turbine. So this value typically is between 10 to 20 kilometer per hour. So the next what we define is rated speed. By seeing the keyword rated here, we can say that the rated speed is the minimum wind speed at which the wind turbine will generate its designated rated power. Wind turbines are generally designed to yield maximum output at much higher air speeds. For example, if I have a 10 kilowatt wind turbine, it may not generate 10 kilowatts unless the wind speed reaches say 40 kilometer per hour, and rated speed of most of the machine is in the range of 40 kilometer per hour to about 55 kilometer per hour. Now we have another term called cutout speed. At very high wind speeds, typically which is above 80 km per hour, most wind turbines will cease power generation and shut down. The wind speed at which this shutdown occurs is called the cutout speed. Now let's solve an example to understand what is the power in the wind present, and using two cases here. So though the average wind speeds is same in both the cases, here we have 6 meter per second, here we have 3 meter per second and 9 meter per second. So the average in both the cases is 6 meter per second. But in the second regime with two different wind speeds of a lower and a higher wind speed, we see that this produces 75% more energy compared to the constant wind speed. What would a typical wind turbine and the corresponding diameter and elevation look like? So we have something from 0.15 megawatt all the way up to 3.5 megawatt, where 2.5 megawatt and 3.5 megawatt are the current state of the art technology. If we go for a 5 megawatt wind turbine where the diameter is about 120 meters and the elevation is about 394 feet or about 400 feet or close to about 130 meters, we'll be having a wind turbine which is much bigger than the wingspan of a Boeing 747. So the power in the wind is half times rho times A times V cube, where this is the air density, this is the cross sectional area of our wind turbine, and V is the speed of the wind. And we have specific power which is defined as PW by A is equal to half times rho times V cube. Let's have a look at the effect of the turbine diameter on generating power. Let's say for a horizontal axis wind turbine, the cross sectional area is pi r square, or is equal to pi by 4 into d square, where d is the turbine diameter. Now we know power in the wind is equal to half times rho times cross sectional area times V cube. For example, if I increase d to 2d, what would be the increase in power? So if I do that, the power PW becomes 4 times PW, because doubling the diameter increases the power available by a factor of 4, while the cost of a turbine increases roughly in proportion to the blade diameter, but the power is proportional to the diameter squared. So bigger machines have proven to be much more cost effective in the case of horizontal axis wind turbine. Similarly, for a vertical axis wind turbine, if you look at this picture here, we notice that the cross-sectional area A corresponds to nearly equal to 2 by 3 times the diameter into H. Here, for a vertical axis wind turbine, you will notice that the increase in power is proportional to just D and not D square. So like we mentioned before, for higher power it is much more cost efficient to use horizontal axis wind turbine, because the cost increase in a vertical axis wind turbine would be the same as compared to the power increase. Now, how does the height of the wind turbine tower affect the power in the wind? So you will notice that wind speeds near the ground is greatly affected by friction that air experiences. For example, if it is the sea like smooth surface, you will have less friction. But if we have a rough surface such as a city with tall buildings, the wind would be flowing with much more friction here. So we have a formula which says that the ratio of the wind speed at height h to height h0 is proportional to the actual height h divided by h0 raised to a coefficient alpha, where v is the wind speed at height h, v0 is the wind speed at height h0, and alpha is the friction coefficient. Now, if you remember, the power in the wind is half times rho times 8 times velocity cube, or the wind speed cube. The power in the wind at a different height for the same friction coefficient here. So I can say P by P0 is equal to V by V0 cube is also equal to H by H0 raised to 3 alpha. These are the standard friction coefficient alpha for different terrains such as smooth hard ground, shrubs at zero point 0.2, then we have a small town at 0.3, and a larger city would be 0.4. So what can we understand from this equation here and this graph here? The graph is actually between the height of the tower and the power ratio P by P0 with relative power with respect to baseline power and at different heights here. When we have a higher amount of alpha, we notice that the power ratio increases much higher for a higher value of alpha. So which means that higher the friction, the greater the effect of tower height in increasing velocity. It means is that, let's say if I have calm water here, so the friction coefficient would be very less, which means that the winds here and the winds, let's say at a much higher height, the difference wouldn't be much between the two of them. But let's say if I have something like a buildings here, so here the velocity would be much less, while at a much higher height you will get much higher velocities there. So what it means is that here the compared to the power P0 here and here, if both of them are same, here whatever P I get and here what P I get, this guy would be much greater here compared to this P here. So similarly, let's see if I can say that at 50 meters height, if I take it for zero point 0.1, I get an increase in power of about 1.1 times. If it is zero point 0.2, I get about 3 times increase in power, while if it is zero point 0.3 alpha, about 4.25 times the increase in. So now let's finish this wind energy video by solving two numericals. The first numerical is an anemometer mounted at a height of 10 meter above a surface shows a wind speed of 5 meter per second. The friction coefficient for surface is 0.2. Estimate the wind speed and specific power in the wind at a height of 50 meter, 15 degrees Celsius temperature and 1 atmospheric pressure. The air density rho is 1.225 kg per meters cube. So what we just found out is that the specific power in the wind at 10 meters and 50 meters, it's about 2.5 times increase in specific power when we go from 10 meters to 50 meters. A 750 kilowatt wind generator with a 48-meter rotor is mounted on a 50-meter tower in an area with 5 meter per second average speeds at 10-meter height. Assuming standard air density and overall efficiency of 30%, estimate the annual energy delivered. Use alpha is equal to 0.2. So the energy would be 955,858.87 kilowatt hour per year.
In summary, we learned how to find out the power present in the wind before we could find the power present in the turbine. We found out what was specific power, then we learned the effect of turbine diameter, and finally we also understood the effect of the tower height on the power. Thank you.